Okay, all right. Well, we'll get started. Happy Monday to you all, and I'm glad you guys are here. All right, so we left off on Friday. We were talking about back propagation, and back propagation was kind of the process we used to figure out the gradients of the loss function with respect to our weight matrices. So remember, the objective here is we want to figure out how to minimize the loss function. So the loss function is going to be the mean squared error, the difference between the actual values y and our predicted values y hat. And we know that y hat depends on the weights that we pick in our first weight matrix and our second weight matrix. Okay, obviously it also depends on the x values and the y values and all of that, but the y hats, the y hats don't depend on y. The y hats are determined by what we have control over is the values we put in our first weight matrix and the values we put in our second weight matrix. And we want to figure out what values to use in these two weight matrices so that the difference between y hat and y is as small as possible. And we said the way we're going to do this is by doing gradient descent. We are going to iteratively take steps downhill so that we can reach the bottom where that the y hats are very similar to y. Okay? And so we said we wanted to find the gradient of the loss function with respect to the first weight matrix, the gradient of the loss function with respect to the second weight matrix. Okay? The loss function being the difference between y and y hats. We're squaring them and we're summing them all up. Okay? Our first weight matrix is 2 by 3. There's 6 values in there arranged in this 2 by 3 matrix, and therefore when we find the gradient will also be a 2 by 3 matrix. It's just a matrix of all of the partial derivatives with respect to each component within the first weight matrix. So W11, W12, et cetera, you have the partial derivative of the loss function with respect to each of these things. Okay, I think it says where we left off. We actually got a little bit farther than this. We found the gradient with respect to the second weight matrix. And I know there's some questions about, when do we do element-wise multiplication? When do we, do matrix multiplication and all kinds of stuff like that? And so a key here is we're guided by a couple principles. One is we know the dimensions, the resulting dimensions that we need, right? We know that the resulting gradient needs to have these dimensions of being arranged in a 2 by 3 matrix. And so that's one key principle. And basically, we want, even whether our matrix, whether our input values x is 1 observation or n observations, when we calculate the gradient, it's always going to have this dimension of 2 by 3. So whether the data you are using to train your matrix is just 1 observation, because you can just use 1 observation to help train your matrix. Okay, you'll have a 2 by 3 matrix. Okay, even if you have 1,000 observations or 100,000 observations, you'll still result in having a 2 by 3 matrix for the gradient here. And so that's what we have. Okay, so with that in mind, that will help us to figure out whether we want to use element-wise multiplication or matrix multiplication or things like that. Okay, so just to kind of review, we'll look up how do we find. We'll just go through some of the steps again for getting the gradient of the loss function with respect to the first weight matrix. And we said the first weight matrix, the result is going to be a 2 by 3 matrix. And so the way we're doing this is we say, all right, well, let's take a look at, we're first going to treat this as a sum, a sum of basically the gradients. Well, we can find the gradient of the sum, and this is going to be the sum of basically all of the gradients. Okay, and so whether we have just one observation, which is what we have here, we're looking at y, the nth observation in y. This will produce a 2 by 3 matrix. This whole thing will produce a 2 by 3 matrix, and I can sum all of them up. And later on, when I'm going to want to get rid of the summation sign, and the result should also be a 2 by 3 matrix. So we're kind of guided by that principle that, we know the dimensions that we want, and we try to make sure that when we do our calculations, we're going to get the appropriate dimensions. Okay, so when we're looking at just the nth observation, we can keep in mind that this is a single scalar value, this is a single scalar value. All right, so we have, and when we take the derivative of this with respect to W1, this over here is a single scalar value. We have the gradient of y hat with respect to W1, and we're going to split that into the gradient with respect to Zn3 with respect to the first weight matrix. The relationship between y hat and Zn3 is that when you apply the function f to Zn3, you get y hat. Therefore, the derivative of y hat with respect to Zn3 is just the derivative of f. Okay, so we're going to have f prime of Zn3 here. And then we want to know, okay, what's the relationship here? Okay, again, all of this, if we ask, well, what is this? This is a single value. This is a single value. And what is Zn3? Zn3 is also, right now, a single scalar value. So that means this entire thing over here has to be the 2 by 3 matrix. Okay, so keeping that in mind, so far, this is all a single scalar value, and then whatever this result here is going to be a 2 by 3 matrix, and that means the product of these two things will also be a 2 by 3 matrix. So if we keep that in mind, we can say, all right, well, what are the dimensions that we're going to need? Okay, so we can say, well, what is the partial derivative of Zn3 with respect to the nth observation in A2? Okay, so we have nth observation of Z3, nth observation of A2, and what is this relationship? Well, we know that if we're looking at just one row, okay, well, actually, just if we're looking at the one row in A2, it's going to be a 1 by 3 row matrix here. Okay, so we have we're looking at one row, and we get three variables in A2 here. Okay, so looking back here, A2, these are the activated values. There's 3 values, and each observation has 3 values here. Okay, and we're multiplying by our second weight matrix, which is 3 by 1. And so when we do this, we get a 1 by 1. And so when we take the gradient of Z3, the nth observation in Z3, with respect to the nth observation in A2, we're going to get the transpose of W2, and that's going to be this 1 by 3 thing. Okay, so this is a 1 by 3. So we have a 1 by 1 multiplied by a 1 by 3, and the overall thing we need is a 2 by 3 matrix. Okay, so right now there's no way for us to kind of pull that off, right? So we have a 1 by 1, a 1 by 3. We know the entire thing needs to be a 2 by 3 matrix. So kind of just revisiting this, we'll take a look at each of these things. Okay, well, this thing, we have this Z2, the nth observation in Z2. This is just, we're applying F to this. Okay, so if we look at this thing is 1 by 3, and so we just have F prime here, which is also 1 by 3. Okay, so I've got this 1 by 3 and a 1 by 3. So this is a spot where we can say, well, if I try to do matrix multiplication, these two things are not going to multiply. And we can ask, well, should I do element-wise multiplication here? And the answer is going to be yes, right? And the reason for this is if we look at all of the components that go into calculating this thing out, okay? If you look at each value in there, it does make sense to do element-wise multiplication. You want to have kind of the first element multiplied by the first element, the second element multiplied by the second element, in order to preserve the fact that we want it to remain, to keep those dimensions of 1 by 3. Okay, so if you think about, well, after this multiplication process, do I want to preserve the fact that the dimensions of being 1 by 3? We can do that. Whereas if we had kind of done a transpose or tried to do some kind of matrix cross product or something, where we do a 1 by 3 by a 3 by 1 or something, that will end up changing. That will end up putting in a summation where you end up getting a 1 by 1 scalar, which is not what we want, because the end result, again, is we want to have a 2 by 3 thing at the end. Okay. We talked about this one's probably the strangest one of all. Okay, so if we think about the dimension of the nth row in Z2, okay, we're looking at one row in Z2. Z2 being you have n rows and three columns. If we're looking at just one row, that's a 1 by 3. Okay, the result here, though, is it's the product of x, the nth row in x, multiplied by our first weight matrix, which is 2 by 3. So if I go back to this beginning part here, we have x multiplied by the first weight matrix. Okay, each row, there's 2 columns. We're going to multiply by 2 by 3, and we're going to get 3 values. So here we are. We've got the nth row in x, which is a 1 by 2. We're going to multiply by the 2 by 3, and that's how we get this 1 by 3 row vector. Okay, and so this is where we are, and we said, well, if we want to take the gradient of the nth row in Z with respect to the first weight matrix, what is the result going to be? It's going to be the transpose of the nth row of x. Okay, so again, when we take a look at this product, okay, this operation of taking the nth row in x and multiplying it by our first weight matrix, we can see that we got a 1 by 2 multiplied by a 2 by 3, and we get a 1 by 3 thing, and we say, well, how does this result change with respect to changes in any of these things, right? So if I change w, if I kind of perturb any one of these things, what am I going to get? It's going to change by a factor of xn1. If I do that to any of the elements in the top row or any of the elements in the second row, it's going to change by a factor of xn2. It's a little bit strange, but we can kind of think of it operating on almost like the sum of this this row vector. Okay, and so the result ends up being the transpose of this nth row of x. Okay, so we end up getting a 2 by 1 matrix. Right, so this is what we have here. And again, the dimensions don't line up. We need to have the result needs to be a 2 by 3 matrix. Okay, and so what I end up doing is I end up bringing this to the front so that we end up getting the dimensions of a 2 by 3 matrix here. Let me give you your first view quiz answer for today. Set up our shop of Shopkins here, I guess. Okay, let me find out what our view quiz answer is. Our first letter is B. B as in bear. B as in bear. Okay, so we have, first view quiz answer is B. B as in bear. Okay, so here we have this. And then if we remove the summation sign, so rather than working with just the nth row, okay, so the result of this, we get what we want, which is a 2 by 3 matrix, okay? And currently, each observation in X each observation produces this 2 by 3 matrix. We're going to, and the total gradient of everything is the summation of all of those 2 by 3 matrices, okay? So each observation produces a 2 by 3 matrix, and then the total gradient is going to be the summation of these. And so if you have 1,000 of these things, it's like each observation gets a tiny little vote in saying which way is downhill, right? So it says, one observation says, to minimize the score for me, you need to go in this direction. And then another observation says, to minimize the score for me, or minimize the loss function for me, you should go in this direction. Another one says in this direction. And so when you add them all up, it's kind of the aggregate kind of vote. Everyone says I should go, over here, and someone says I should go over there, and someone says I should go there and there. And then kind of like if you take the sum of all of these vectors, or all of these gradients, and each gradient is effectively a vector in 6 dimensions here, you're going to get the, thank you, the summation of everything here, okay? And so what we're going to do is we're going to, rather than just looking at the nth row and summing them all up, okay, we're going to see if we can just kind of drop the subscript and look at the entire X matrix and take advantage of the matrix multiplication, which does the summation implicitly as part of the multiplication operations here. All right. So, unfortunately, when we've done this, okay, each of these things which have a subscript n will change dimensions to be, go from one row, 2 by 1, or I guess one row transpose, 2 by 1 to 2 by n, and this will become, the y's will become n by 1, and so on and so forth. And so we can take a look, and again, when you think about, well, I need to preserve this, these dimensions here. I need the resulting product of this and this to remain n by 1. That is when you want to use element-wise multiplication, okay? Because if you don't use element-wise multiplication here, and you try to, transpose it or something, it's going to reduce it down to just a single value here. So we want to preserve the fact that this product remains, keeps these dimensions of n by 1, right? And so we're going to put element-wise multiplication here. We want to preserve the fact that this product and this product remains n by 3, so that this times this ends up being 2 by 3. And so that's why we're going to put element-wise multiplication here. So this is going to be the resulting gradient, 2 by 3, and this handles all of the summations there. Okay, so now, so this is the hard part, okay, and of arriving at these results here. And in your next homework assignment, I know you guys are still working on homework 2, and then you're studying for the midterm. And I'll send out a seating chart, by the way. So as you guys are all working on that, homework 3 will be eventually making its way. And in homework 3, you'll have to figure out the gradient with respect to our bias matrices. All right. All right. Okay, so let's code this up. All right. Now you say, well, how are we going to turn this all into code? Actually, the coding, once you have all of this work done, the coding is rather easy and straightforward. I know it's a little bit maybe it's hard to imagine. Okay, but the math part's the hard part. The coding part's actually the easy part. Okay. And so we'll take each element and we'll just turn everything into a function, okay? Because a lot of times when I say, hey, code this thing up, if you think about like, what did you do in 102A? And I said, code up the coordinate descent algorithm, you might have been like, oh, that was, I don't know, maybe it was easy, or maybe it was a huge pain, okay? So it's like, oh, go ahead and code up this neural network, and I'm telling you it's easy. Okay, well, first of all, here we'll write a function for the sigmoid function. Okay, 1 over 1 plus e to the negative t. And so here I'm just going to write a function. We're using z. And I got 1 over 1 plus e to the negative z. All right, so this is a straightforward thing, right? So if I said go from here to here, you guys could do this, okay? We're going to put in our input matrix, okay? Our input matrix, our X matrix, is we had 3 observations in 2 columns. And these were the observations. So I'm just saying, okay, I've got 3, 5, 5, 1, 10, 2. And to make a matrix out of that, I'm just going to say I want 2 columns and the data is coming in by rows. The y values are in a matrix 75, 82, 93. And in order to get this to work, I need to kind of scale my values down. And the values in y, we need to kind of get them between basically 0 and 1, because the result of the sigmoid function always produces a value between 0 and 1. And so there's lots of ways we could have done this. I'm going to just take each of these numbers, 75, 82, 93, and divide by 100, and that does the job of getting them between 0 and 1. Now, if somebody wants to scale them a different way, that's fine. It kind of makes sense. If our y values are test scores where the max value is 100 or something, it kind of makes sense. Okay. And now, here I'm using these variables: input layer size 2, output layer size 1, hidden layer size 3, indicating how many nodes we have in each of these things. And by using variables, this gives our network some flexibility. So later on, if I wanted to change the hidden layer size to, say, 10 nodes, I can just change this from a 3 to a 10, rather than having to change everything everywhere. All right, so when we do forward feed, this is what the operations look like. We take our input matrix X, multiply it by our first matrix W. We then apply the sigmoid function F to the resulting Z. And then we take that result, A2, multiply it by our second weight matrix, which gives us E3. We apply the sigmoid function F to that, and we get our y hats. So forward feed is just a matter of turning this into that, okay? So here I'm going to create 2 weight matrices, W1 and W2. W1 is 2 by 3, or the number of rows is our input layer size, and the number of columns is our hidden layer size. Right now I'm just putting in the number 1s, just repeating the number 1s. I think later on I just put some random values in here, okay? Random, like between 0 and 1, random uniform values in there, and that seems to work, okay? W2 is hidden layer, which is 3, by our output layer, which is 1, so this is going to be 3 by 1. And so forward feed is just these matrix multiplication operations. X times W1 produces, I'm going to call this Z2. I apply sigmoid to Z2, and that gives me A2. A2 times matrix multiplied by W2 gives me Z3, and sigmoid to Z3 gives me Y hat. So this is just a matter of doing these operations right here. Our cost function is y minus y hat. We're going to square that. We're going to sum it. And then right now I have it multiplied by 1/2, but I mean, I could even just leave out this constant. It doesn't really make a difference. Okay. So right now, the cost, our loss function, the difference between the actual values y and y hat, is just some number that is kind of meaningless right now. But all we know is that we want this value to shrink. Okay. We want to minimize it. We want this value, this cost value, to shrink. All right, so we're going to do our back propagation. And so we need to calculate the derivative of the sigmoid function, which is going to be e to the negative z divided by 1 plus e to the negative z quantity squared. Right? And that's from, I don't know where it was. Okay, actually it's not in this lecture. Okay, but it's somewhere in the notes. This was the sigmoid derivative of the sigmoid function f prime. All right, so let's do this first thing. Okay, we'll do dj dw2. Okay, so first I'm gonna say delta 3 is kind of this product right here. So I've got y minus y hat. This is element-wise multiplication, so that's just the asterisk. Element-wise multiplication of Z3. So I've got negative y minus y hat times this, okay? And we want to multiply that by A2 transpose. So I'm going to do A2 transpose, matrix multiply delta 3, right? And so this is just, I'm just going straight from the work that I've done into the work right here. And then for dj dw1, we do something similar, okay? After some work, we said, okay, we have x2 times d3 times w2 transpose, et cetera, et cetera. So delta 2 is delta 3 times w2 transpose, element multiply sigmoid, or the f prime of z2. So here I've got delta 3, which we calculated on the previous slide, matrix multiply by w2 transpose, element-wise multiplication with sigmoid prime z2. So that's delta 2. And then dj dw1 is x transpose delta 2. So I got x transpose times delta 2. All right, so this is kind of just a literal going from this into code here. And it's always good to kind of just double check to see if our thing works. And check all of our matrices, okay? So to get this to run, here, and actually, I'm going to switch over into the code here. So I have all of this code. Let me, oops. So I have all of this input stuff and input layer. So all of these things that I've been writing on the slides, we have cost function, our current cost function, and we sigmoid prime. Okay, we can skip that. All right, and so here we want to kind of, right now, this is just to check, you know, is it multiplying? So our current gradient, dj dw1, is indeed a 2 by 3 matrix, the gradient with respect to w1, and we want the gradient with respect to w2, we want that to be 3 by 1, and indeed we do have that. Okay, right now it's kind of junk, and then we want to see to do gradient descent, we take our current values of w1, subtract off a scalar times dj dw1. Okay, and I think right now my gradients, or my weight matrices, are just full of 1s. Okay, but we're going to just for gradient descent, we take our current values, subtract off the scalar times the gradient, and same thing for w2, take our current value, subtract off the scalar times the gradient. Okay, and so now w1 gets updated, w2 gets updated. I might have done that twice, but we can see, did the cost function go down? Whoops. Hang on, I clicked the wrong button. So earlier, our cost function back here is 0.01532851, and then what we're hoping is that, oh, you know what? I think I've already updated my W's. Okay, so actually, let's see. Earlier, as I scroll through here, this was our cost, 0.01532851. After updating, did it update? No, maybe not. Oh, we're going to get our new y-hats. Now that we've adjusted what W1 and W2 are, we'll calculate what our new y-hats are, and we'll see if there's a difference between the old y-hats and the new y-hats, the two costs. Okay, so cost 1 was 0.1532851, and what we're hoping for is that cost 2 is smaller. Okay, and it is. It went from 0.15 down to 0.12. Okay, so that's a success, right? So because the idea is after we take a step using gradient descent, the cost shrinks. Okay, so that's promising. Now, I don't have this in the notes, but I wanted to show you numeric gradient checking here, okay? Okay, so the way numeric gradient checking is going is the idea here is we want to see, did we code this up correctly? Okay, and we're going to try to do this in a manual way, right? So what I'm going to do is I'm going to add a tiny little thing to each element in my weight matrices, and we're going to see what effect does adding a small perturbation to each element does, what effect does it have on the resulting cost? Okay, so this is the way numeric gradient checking works. Okay, so I'm going to kind of just clear everything out. So W1 and W2, I'm going to just kind of reset to just be all ones. Okay, I mean, we could start off with just something else. And I'm going to say, all right, what are our y-hats, and what is the kind of current cost with these current weight matrices? So I've got W1 and W2. I do forward feed, x times W1, sigmoid applied to Z2. I get my y-hats, okay? What are my y-hats? My y-hats are this, okay? And we want to compare that where the actual y's are this, and we say what is the cost between our y's and our y-hats, okay? So we do our current cost, and again, our current cost is 0.01532851, okay? And now what I'm going to do is I'm going to add 0.0001 to each element in W1, but I have to do this one at a time. So there's 6 elements in W1, and so I'm going to add 0.0001 to the first element in W1, okay? So here I'm going to just create an empty matrix to help me figure out the numeric gradient, okay? So right now, this is just the elements of the numeric gradient, okay? I've got 6 elements here. And so for the very first one, okay, I start off with, let me just do this for I equal to 1. Okay, we're going to just do kind of within this loop, just for I equal to 1. Let me just show you what's happening. So I reset W1 and W2. W1 is all ones. W2 is all ones. And here I'm going to just add 0.001 to the first element in W1. So if I look at what W1 is now, okay, W1 is 1.0001 for the very first element. Everything else is still a 1. Okay, so using this is my updated W1. I'm going to say, all right, let's figure out what our new y-hats are. Okay, so using this, I say x times W1, sigmoid to Z2, A2 times W2, sigmoid to Z3. I get my new y-hats. How has y-hat changed? Okay, so my old y-hats back here was 0.913, 5289, 0.88127, 0.9173. Okay, and then after adding 0.001 to this first element, how has it changed? And it looks like, well, I don't know. Did it even change that much? Maybe, maybe not. I'm not sure. So here I'm going to calculate the cost using the new y hats, okay? And we're going to compare that to kind of the current cost, all right? And so we can see, oh, you know what? The cost did change just ever so slightly. It went from 0.01532851 to 0.01532863. Okay, so just a very small change. And that's expected because all I did was just add a tiny little 0.0001 to this first element here. So I'm going to just say, all right, how much did it change? We divide by the size of how much I added, 0.001, and we're going to store that into the kind of the first element in our numeric gradient. So right now, our numeric gradient, W1, has this calculated for what is the gradient for the first element there, okay? And then I go through and I do the same thing for I equal to 2. Okay, so I'm going to do I equal to 2. And then, so now I reset W1 and W2. W1 is all 1s again. W2 is all 1s again. And I'm going to add 0.0001 to the second element in W1. Okay? And so W1 now, only the second element, this one is now 0.001. Okay? And I go through, I calculate what are my new y hat values, and then what's this, and then so now the y hat values changed ever so slightly, and so now I've populated this thing. Okay, does this kind of make sense what I'm doing? So I'm just going through there's 6 elements in W, and for each one I'm going to just add 0.0001 and say what effect did it have on the cost, and using that we're going to kind of get just an estimate of the gradient. All right, so I'm going to go ahead and just run the loop. All right, for W1, there's 6 elements, and it runs through all 6 elements in W1. I'm going to do the same thing for W2. There's 3 elements in W2. Okay, and so my numeric gradient for W1 looks like this. And my numeric gradient for W2 looks like that, okay? And that's fine, all right? And then here we have the gradients found using our analytic approach. We kind of did the gradients using the derivatives, and we said, okay, well, what do we get here, all right? So what we want to do is we want to compare, is my analytic gradient, is that close to my numeric gradient? So this is my analytic gradient, dj dw1, using kind of the formula that we did, you know, y minus y hat, sigmoid prime, et cetera, et cetera, et cetera. And we compare that to my numeric gradient. The numeric gradient was found by adding 0.0001 to each element and seeing what effect it had on the cost function. Okay, so what we're hoping is that these two things are similar, and they are. We have 0.00121, and I got 0.00121, and maybe the last 3 values, 512 becomes 406. Over here I have 0.002397, 0.002397, 309 versus 250. They're overall pretty close. They're off by a tiny bit, but overall they're pretty close. Okay, we can do the same thing with the gradient with respect to the second weight matrix. So when we did it analytically, we get 0.0136646. When I did it numerically by adding 0.001 to each thing, I get something very similar, 0.013664425. Okay, so we're off just by a tiny bit. So this is a good sign. Okay, and this is kind of a way to make sure that when you did your math, you did it right, because the numeric gradient check is kind of like, it's like almost guaranteed to work. You just add a tiny bit and you say, well, how much did the thing change? Okay, so anyway, we can kind of just see, you know, what's the difference. These are off by a factor of, you know, 10 to the negative 5, 10 to the negative 6. Okay, so here we'll go ahead and I'm going to just start off with some random starting values for our weight matrix. So rather than just all 1s, I just picked 6 random values and 3 random values for a second weight matrix. And we're going to go ahead and just run this using gradient descent. So I'm going to just do 10,000 steps starting at my location, and at each iteration I calculate the current y hats, I calculate the gradients, and I update my W1 and W2 matrices using the gradients. Okay, So this is the entirety of training a neural network. Okay, so a lot of times when you use a package like TensorFlow or PyTorch, you can run the functions to train the neural network, but it feels a little bit mysterious, like what's happening underneath the hood. But this is the entirety. Okay, at least for our simple simple neural network. First, we take our current values. Oh, my battery's running low. Oh dear. Okay. Class is almost done anyway. So we take the current weight matrices W1 and W2, and we do forward feed to get our current estimates of y hat. And we need those estimates of y hat to get to figure out what our gradients are. Okay, so we use that. We calculate our gradients, and all of these, if you look at them, they're just matrix multiplication operations, or maybe the application of some kind of function. Here I'm applying a sigmoid function, but it could be any other activation function. So these are just matrix multiplication operations. This is the forward feed part to calculate the y hats. We calculate the gradients. We do that, and then we update the current weights by taking our current weight matrix and subtracting off some scalar multiple of the gradients. And so I'm going to go ahead and just do 10,000 iterations. Okay, and it's done. And we can say, all right, the resulting weight matrices look like this. So W1 has these values. W2 has these values. These values are pretty much meaningless to us. Okay, it's not like linear regression where you get coefficients and you understand what they mean. Here, the coefficients in your weight matrices, they're pretty much meaningless. But what we're hoping for is the predictions y hat are similar to the actual values of y. And that, it has succeeded. Okay, we had 3 observations. The actual observations are 0.75, 0.82, 0.93. And our estimates, after 10,000 iterations of training our neural network, are very close to that, 0.74999, 0.82005, 0.92989. Okay, so pretty close to the actual values. We can say what is the cost of our estimates, and we're at 10 to the negative 9. That's pretty good. And we can kind of take a look. What we've been doing is every time I calculated the cost, I've been keeping track of this in what we call the cost history. And so I can say, all right, let's just take a look at this plot here. And what we can see is there was, in the beginning, all of our steps rapidly dropped the cost. We hit kind of a plateau, and then we found somewhere a way to drop it off, and then we've kind of been stuck in this not much improvement here, okay? I can take the log of the cost, which helps us see what kind of improvement we're getting here. And so we see, okay, drop, flat, not much improvement for a while. And then over here, where it looks flat, this is actually just very incremental improvements in terms of it's, maybe 90% every single step we're getting some improvement there. Okay. Okay, I guess we're out of time here. And all right, so let me give you your last 2 view quiz answers. The last 2 view quiz answers today are the letters E as in elephant and A as in apple. View quiz answers 2 and 3 are E as in elephant and A as in apple. Okay, E as an elephant, A as an apple. There you go. All right, well, I appreciate your flexibility regarding our special guests today. And good luck as you study. We will see you on Wednesday for the midterm exam. Good luck.